Then next point, that is reflection of longitudinal wave. Consider longitudinal wave traveling from a rarer medium to denser medium. In longitudinal wave, compression is high pressure region while rarefaction is a low pressure region. When compression reaches the denser medium, it tries to pull the particle of medium, but the energy of particle in the rarer medium is not sufficient to compress the particles of denser medium. According to Newton's third law of motion, an equal and opposite comes into play. As a result, the particles of rarer medium gets compressed. Thus, when longitudinal wave travel from rarer medium to denser medium, a compression is reflected as compression and a rarefaction is reflected as rarefaction. So there is no change of phase during the reflection, which we can see in this figure. Compression is reflected as compression or rarefaction is reflected as rarefaction. So when longitudinal wave travels from a denser medium to rarer medium, okay, which we can see in this figure, okay. When longitudinal wave travels from a denser medium to rarer medium, a compression is reflected as rarefaction. Here reversal of phase change takes place, that is phase changes by pi radian. Compression is reflected as rarefaction or rarefaction is reflected as compression. So when compression reaches a rarer medium from denser medium, it pushes the particles of rarer medium. Due to this, particles of rarer medium get compressed and move forward and rarefaction is left behind. So thus a compression is reflected as rarefaction. Similarly, rarefaction gets reflected as compression. Okay, so that is phase change by pi. Now, superposition of waves. So superposition of wave is nothing but what? Okay, we have to add them, two or more waves, which we will see it. Suppose you wish to listen to your favorite music. Is it always possible, particularly when there are many other sounds from surrounding disturbing you? How can the background sounds be blocked? Of course, the mobile lover generations use headphones and enjoy listening to its favorite music. But you cannot avoid the background sound completely. Why? So that we have to study superposition of waves. Now, we know that sound waves are longitudinal waves propagating through an elastic medium. When two waves traveling through a medium cross each other, each wave travels in such a way as if there is no other wave. Each wave sets particles of medium into simple harmonic motion. Thus, each particle of medium set into two simple harmonic motions due to two waves. The total displacement of particle at any instant of time during traveling of these waves is the vector sum of two displacements. So there is an addition of two waves. This happens according to the principle of superposition of wave, which states that, so this principle will be, when two or more waves traveling through a medium pass through a common point, each wave produces its own displacement at that point, independent of the presence of the other wave. So the resultant displacement at that point is equal to the vector sum of the displacement due to individual wave at that point. As displacement is a vector, we must add the individual displacement by considering their direction. There is no change in shape and nature of individual waves due to superposition of waves, and this principle applies to all types of waves like sound waves, light waves, waves on a string, etc. And we say that interference of waves has taken place. So here are some examples we have to see. Okay, so we will see these examples. Okay, let us consider superposition of two waves pulse into two different waves. So superposition of two wave pulse of equal amplitude, same phase moving towards each other. So see this figure 6.6, equal amplitude and same phase. Now, propagation of approaching wave pulses, their successive position after every second, their superposition and their propagation after superpositions are shown in figure 6.6. So there are a total 7 figures, 6 point A, B, C, D, E, F, G. Okay, how this wave is generated. Suppose two waves cross each other at t equal to 2 seconds. Okay, that point C. Okay, and t equal to 4 seconds. Okay, so which is at point E. Okay, so figure 6.6 C and D and E. Here two waves pulse superpose. The resultant displacement is equal to the sum of displacement, that is full line, due to individual wave pulse, that is dashed line. Okay, see this figure, dashed line. Okay, in figure D. This constructive interference, this is nothing but constructive interference. The displacement due to wave pulses after crossing at t equal to 5 seconds and t equal to 6 seconds, which will be in F figure. Okay, and G. So after crossing each other, both waves pulses continue to maintain their individual step. And one more thing that is about opposite is superposition of two waves. Okay, here you can see two waves pulse of equal amplitude but opposite phase moving towards each other. In first figure phase was same, here phase was opposite. So equal amplitude and opposite phase. Okay, see what will happen. The propagation of approaching wave pulses, their successive positions after each second, their superposition and propagation after superpositions. Okay, see here only 5 figures are there, A, B, C, D, E. So these wave pulses superpose at t equal to 2 seconds, and the resultant displacement, that is full line, is 0. Okay, see due to individual displacement, that is dashed line, differing in phase exactly by 180 degree. So this is destructive interference. So crest trough overlapping, that is destructive interference. Displacement due to one wave pulse is cancelled by the displacement due to other wave pulse when they cross each other. So that is nothing but your destructive interference. So after crossing each other, both the wave pulses continue and maintain their individual shapes. Okay, so that is nothing but your superposition of waves. So in this first figure 6.6, okay, which we can say this is your constructive interference, and about this it is your destructive interference. So in shortly, which we can say that, okay, in constructive interference, crest overlap, or rarefaction, compression. But in terms of destructive interference, crest trough overlap, which will cancel out each other. Trough crest also overlap, they also cancel out each other. In terms of longitudinal, you can consider compression rarefaction overlap, rarefaction compression overlap. So these are the examples of superposition as well as constructive and destructive interference also, which we can say shortly. Fine. Okay, thank you. Amplitude of resultant wave product due to superposition of two waves. Already this type of equations we have seen in oscillation, equation of motion. Same type of equation we have to study here. Just we have to consider that phase difference by phi. So consider two waves having the same frequency but amplitude A1 and A2 are different. Let these waves differ in phase by phi. The displacement of each wave at x equal to 0 is given as, so y1 is equal to a1 sin omega t, y2 is equal to a2 sin omega t plus phi. So this phi is additional term in second equation. Then according to principle of superposition of waves, resultant displacement at x equal to 0, we have to add them, that is y is equal to y1 plus y2, or y equal to a1 sin omega t plus a2 sin omega t plus pi. Now omega t plus pi, this is nothing but sin a plus b, so we have to expand it like sin a cos b plus cos a sin b. So it will be a1 sin omega t plus a2 sin omega t cos pi plus a2 cos omega t sin phi. So collect the same terms, that is sin omega t. So y equal to a1 plus a2 cos phi into sin omega t plus a2 sin phi cos omega t. If you write a1 plus a2 cos phi is equal to cos term and a2 sin phi is equal to a sin term, okay, then we can write this equation y equal to a cos theta plus sin omega t plus a sin theta cos omega t. So it will be what? Again, it will be a sin of omega t plus theta, that is it will be sin a plus b. So this is the required equation, y is equal to a sin omega t plus theta, which is the equation of resultant wave. It has the same frequency as that of the interfering wave. So omega is what? Angular frequency, which is also same. A is a resultant amplitude, okay, t is time, and theta is, we have taken the phase difference, that is. Now amplitude A can be calculated by squaring and adding equation 6.4 and 6.5. So what is this addition? A square cos square theta plus a square sin square theta, which is equal to 1. So that will be your a square, is equal to a1 plus a2 cos phi bracket square plus a2 square sin square phi. Now a square is equal to what? a1 square plus 2a1 a2 cos phi plus a2 square cos square phi plus a2 square sin square phi. So sin square plus cos square is equal to 1. So it will be a1 square plus 2a1 a2 cos phi plus a2 square. So if you calculate its square root on both sides, it will be a equal to under root a1 square plus 2a1 a2 cos phi plus a2 square. So this is the value of resultant amplitude. It depends upon phase difference also. So again here we have to study special cases. So there are again two cases when phi equal to 0, waves are in phase. The resultant amplitude a equal to what? Okay, then we have to put phi equal to 0, so cos 0 is 1. So it will be a1 square plus 2a1 a2 plus a2 square, that is a plus b bracket square. So it will be a1 plus a2 bracket square in square root. So if you calculate square root, it will be a1 plus a2. So the resultant amplitude is maximum when phi equal to 0. If amplitude of waves are equal, that is a1 equal to a2 is equal to a, then resultant amplitude is 2a, because a1 plus a2 is equal to 2a. When phi equal to pi, now we have to consider second case, phi equal to pi, okay, waves are out of the phase. So here we have to consider cos phi is what? Pi. So cos pi is minus 1. So it will be a1 plus a2, a1 square plus 2a1 a2 cos pi plus a2 square. If you take a1 minus a2 bracket square, so that will be same term. So a1 minus a2 bracket square in square root. If you calculate square root, its value will be a1 minus a2. So the resultant amplitude is minimum when phi equal to pi. So in this way you can notice here phi equal to 0, okay, then amplitude will be maximum, okay, that will be 2a, and when phi equal to pi, amplitude will be 0. So a1 is equal to a2 is equal to a, resultant amplitude is 0. So maximum amplitude is the sum of two amplitudes when phase difference between two waves is 0, and minimum amplitude is the difference of two amplitudes when phase difference between two waves is pi. So if you consider phase difference 0, phi equal to 0, it will be maximum, and phi equal to pi, it will be minimum. Then the intensities of waves are proportional to the square of their amplitude. So when if you consider phi equal to 0, then intensity is proportional to the square of amplitude. So that is nothing but a1 plus a2 bracket square, and when phi equal to phi, a1 minus a2, that will be 0, so it will be a mean bracket a mean square. So intensity is maximum when two waves interfere in phase, then it will be maximum, while intensity is minimum when two waves are interfere out of the phase. So when they are in phase, okay, its intensity will be maximum, and when they are out of phase, their intensity will be minimum. Okay, so keep in mind this difference. In phase, so intensity is maximum, and out phase intensity will be minimum. And again we are going to learn this topic, okay, about superposition of waves in chapter 7 on wave optics. So same term we have to study in next chapter.